I was a little bit worried being one of the later speakers during this session today, in the sense that I expected many things to be said already before it was my turn to say something. This is partly true, but on the other hand, I think this also formed a very nice introduction. And this was the first slide actually where I hesitated a lot whether I should include it because I was scared that many people would use it. But I think it illustrates very nicely the development in projections over sea level over the last 5 years, because this is a plot from the AR4 report, and this AR4 report presented results in terms of global average sea level for different scenarios, with the big caveat being excluding the effect of the recent dynamical changes in ice sheets. And I think what we'll see now during this presentation is the progress which has been made over the last 5 years, being that we are making our first attempts in quantifying the dynamical change in ice sheets, and that we also make our first attempts in making regional sea level change projections. And as Giorgio introduced this morning, and as well as Detlef, in fact, there are two major arguments why we should go to regional sea level changes. One is, first of all, that the climate change is variable, so the steric and thermosteric and halosteric effects, they vary in space. And on the other hand, we have that the mass change leads to a gravitational and a rotational effect, as Giorgio explained, being also a justification to move on to regional sea level changes. And here you see this fingerprint figure for Antarctic, Greenland and mountain glaciers from a paper by Mitrovica et al. In 2000. So just this gravitational effect, it was explained by Giorgio, but what you see is if the ice mass melts, and that's why I show it, because there is a spatial scale in this plot, the sea level will increase on average, but close to the ice sheets it will decrease, and further away it will increase. And you can see on the spatial scales here that if you are within a radius of 2,000 kilometers, then the relative sea level change will be negative, and between 2 and 7,000 then you will be between 0 and the eustatic mean, and further away it will be above the eustatic mean. And that's in this last region. Then on top of that we have the rotational effect, which is important, and that was explained by Giorgio, and this all refers to all ice mass changes which we have. So it's not only the land ice, but luckily also in the last presentation there was some information on terrestrial water changes, and that is also a mass change, so there's also a gravitational effect on those effects. So the main contributing processes which we take into account is the land ice melt, that's then both from ice sheets and glaciers, terrestrial water storage changes, glacial isostatic adjustment, ocean density and dynamic effects. So all effects which have been discussed quite extensively over this day. And as far as possible we try to include them. And the glacier contribution is one of these effects which we take into account. And for that we use information from the CMIP5 models, or from any climate model you could use, temperature and precipitation fields. And if you know where the glaciers are, so you need a local database of all the glaciers, you can calculate with the volume area model volume changes and hence mass changes of the small glaciers distributed over the entire globe. And from that you can calculate the gravitational and rotational effects, and you can see which areas contribute most to sea level change. And if you do that, you can see, for instance, in this lower diagram, that major changes are from North Canada, and the disputed part is the part from Central Asia, where there is a lot of papers about more recently. Then we have the terrestrial water changes. As introduced by the previous speaker, there are two major processes, being the amount of dams built and the groundwater extraction. And the two are partly compensating each other over the past, but definitely not over the future, according to the papers, like for instance the paper by WADA. and where the dam contribution decreases, whereas the groundwater contribution increases. So you get the divergence of the two components with a positive contribution from the terrestrial water changes in the coming century. The glacial isostatic component is an interesting one because it is assumed to be constant over the next century, but there is definitely a spatial pattern in it, as you can see here, which is a composition of the data made by Dick Peltier and Kurt Lambeck. And then the ocean component is the component which probably has been discussed most extensively here during this day, because it is purely driven by the climate models. And it includes temperature changes, salinity changes, but also the effect of these changes on the ocean circulation. And here you see an example, which is an old example from the CMIP3 A1B scenario. And of course, we have now moved on to the CMIP5, as I will show you in a minute. So all in all, we get this important overview figure, I would say, because this wraps up basically what we've heard today. There are changes in sea level to be expected which are related to mass change, which is in this left diagram, and there are changes which are related to volume changes. Most of the changes are driven by CMIP5 climate data, so from the CMIP5 database, which contains roughly 21 or 24, something like that, climate models which can be used to do this kind of calculations. You can calculate the glacier contribution, you can calculate something on the surface mass balance of the ice sheets, and you can calculate the terrestrial contribution. This forms what I would say the climate-driven part of the mass change, and then on purpose you see this one slightly separated from the other components, which is the dynamical contribution of the ice sheets, which is, there's a lot of discussion on that, but in this study we at least take it independent of the climate scenario, because it's not directly driven by climate change, but also to internal dynamics of the ice sheet. So there is a lot to say for taking it independent of climate model results. And these components, they feed in the sea level equation model, like a model as Selene is, discussed by Giorgio this morning. And from that you get a regional pattern of the mass changes over the entire ocean. And at the same time you calculate directly from the CMIP5 the steric component. There's one which has only shortly been mentioned, I would say. That's the inverse barometer effect. So the air pressure changes over the next century. It's a small effect, but you can take it into account. Wind effects, I will come back at the very end of my presentation, but they are not included in this main results you will see here. There's the GEA effect, which is also independent of the climate system. It's a constant in time, but with a spatial pattern. And then tides are also not included in the projections, but they play a role in the attribution issue of the regional patterns in sea level. Because if you add up all these components, you finally get the distribution of the regional pattern in the sea level change for the next century. But I would say that the first thing you need to do, in fact, is to check out in the past whether you can really explain also the regional patterns in the sea level change. And we have been trying to do that also, and I only show one slide, but in that slide the tides play a role, not an important role, but they play a role in the interpretation of the data. So what you see here is a compilation over the last 50 years from the tide gauge record for 17 different regions in the ocean. And what we did is we tried to simulate, based on what we know about the ice mass changes and about the steric component, what the sea level should be at the tide gauge location. And what you see here are different regions, and in blue you see the tide gauges, and in red you see the modeled results. And there are a few regions where there is a very consistent result. model and tide gauge records are in a very good agreement. There are regions where there's absolutely no agreement between the two, and well, a lot of the regions, the error bars are so large that you cannot draw many conclusions, I would say. The sign is different, but the uncertainty is so large that you cannot exclude that the model is in agreement with the tide gauge record, I would say. And for many regions, it is within the 1 sigma uncertainty between the model and the data. So, yeah, you can criticize this a lot, but I think there is, and I fully agree that much more needs to be done in this field, but it looks like we will be able in future to really get to the regional attribution of the sea level rise. So I think that is a justification for continuing with also projections on the regional level. So back to the projections, you see here a result from the projections for the different components in the upper left graph. So this is for the RCP 4.5 scenario, and it is the contribution from the small glaciers and ice caps and ice sheets by 2100. You see the same, but then for the steric dynamic contribution and the atmospheric loading grouped together. So the direct climate model effect, you may call this. The groundwater contribution, which is here taken from A1B scenario because it was not available for the RCP scenarios yet, but A1B is fairly comparable to RCP 4.5, so it's not too bad to combine that. There is an ice dynamical contribution, giving a distinct pattern, of course, with around Greenland and Antarctica, and there's the GIA pattern. And these figures are made by Mark Carson from Hamburg. So the nice thing I would say also is that if you try to combine them all in one modeling framework, that you can also compare the uncertainties of the different components, and that is what this figure shows you. The same components, but then in terms of uncertainty rather than the projection and the addition to future sea level rise. And one thing which was implicitly mentioned, I would say, this morning was that the spatial variability is dominated by the steric pattern, but of course there is there's a smaller scale variability in the steric pattern, but on the other hand you see that it's the same time color scale, that the variability in major parts of the ocean is dominated by the uncertainty in the ice sheet contribution, because that is maximized far away from the ice, and as the order of magnitude of the steric component and the ice sheet are globally more or less equal, it means that in the far field, far away from the ice sheets, the ice sheet dynamics will dominate the uncertainty in the projections. And the other ones, they only have a large uncertainties in the areas where you have the major groundwater extraction or the major GIA signal, and they're not important in major parts of the ocean. So you can also sum up, of course, this different components, and that is what you see in the upper graph here. You see the contribution, the total contribution for the 4.5 scenario, adding up to a little bit more than 50 centimeter and an uncertainty of 18 centimeters. And because we now have so many climate models, I think we can start to discuss also on uncertainties, and that is why we have also made a 90% confidence level value for the regional pattern. And you can see that the uncertainty in the regional pattern varies also very much from place to place, and that is an important notion, because eventually it's only the local sea level which matters, and not the eustatic mean value which matters. And an interesting issue also is that you can see that in the global mean, the glaciers and ice caps are roughly identical to the steric component, and also if you would add up the ice sheet component. So there's not a single component which overrules the total effect in the dynamics. And on the other hand, it's also true to say that all the different effects, even the GIA, may dominate the local value for the projection. So you really have to take them all into account, and there's not a simple way to reduce the uncertainty in regional sea level. You really have to work on all the different components. And here you see then eventually, for instance, an interesting result. If you subtract the mean value from the projected value, you get the relative anomaly at the different sites. And you can, for instance, see that sites like the east coast of the US, they get definitely more sea level rise than the global mean value. And sites around Antarctica and Greenland, they have definitely a much lower sea level rise than the average over the entire ocean. And if you express that for the different scenarios, the RCP 4.5 is the blue one, and the 8.5 is the red one, you can also see that there is a skewed distribution, and that is skewed in space, and that is related to the fact that the gravitational effect only has an effect of, say, 25% extra in the far field, but locally, close to the ice sheet, it may have a very strong negative effect. So you get more values which have a sea level rise lower than the average. And that may also be much more below the average than the higher values are above the average. So if we look to the different oceans, we have different points here for illustration. The Arctic Ocean, and the North Atlantic 2, 3 is the Equatorial Pacific Ocean, and 4 is the Southern Ocean. You can see that in the Arctic Ocean, the signal is largely dominated by the steric component, which is clear because you're close to where the ice melts, so you may expect that the ice component, given by this blue bar, is much lower than the average blue, which is this dotted line, and clearly the steric component is more important in that area. And the climate models have a large spread in the steric contribution in the Arctic region, and as a result you see a large uncertainty for this region. And here you see then the total sea level rise in the Arctic region, which is lower than the average given by this dotted line again, which is in black. If you go to the North Atlantic Ocean, you see that the ice component and the steric component are much more in balance because you're already further away from the ice. And in the Equatorial Pacific, there the ice component is the dominating component because that's what we call far field for the ice sheet contribution. So you can see that the contribution from the ice is larger than the global mean value in the Pacific. And then we have finally the Southern Ocean, which is far enough from Antarctica to have still a large contribution from the ice component. So if we look to the progress from the AR4 to the AR5 report, which is on its way, we can compare, for instance, the CMIP 3 runs, which were used in the AR4, and the CMIP 5 runs, in slightly different scenarios, but you can clearly see in these figures that the spread in the models is getting smaller, particularly in the Southern Ocean. So we can consider that maybe as an improvement of climate models, but that there is still a considerable spread in the Arctic Ocean, which is clear that that models will vary quite a bit in that area. And overall, you may say, well, the differences are not so large, but you can now see that there is a larger uncertainty which is related to the fact that we now include an ice dynamical component which was not included in the AR4 report. So The steric uncertainty is maybe smaller in the newer results, but that's in a way overcompensated by the fact that the ice sheet contribution leads to a larger uncertainty, but it's not completely comparable because it in fact was not included in the AR4. You can also, if you wish, try to go to a very local scale and to see what happens at the different locations. So we've taken a couple of coastal sites in this graph from north to south, and the last one is the global mean value. This is again for the RCP 4.5 scenario, and this is the mean, and you can see that there are a couple of sites which are above the mean because all the components work in the same direction in those sites. Or, yeah, you should not take it too literally, in those regions, I would say, because the steric component is relatively large there. Land ice is not very small, and there is still a GEA component working in the same direction. So on the other hand, there are also regions where it's far below because you're close to ice and the GEA component is also negative. So I think if we draw a couple of preliminary conclusions, we can say that the tide gauge records can partly be explained by combining models and observations of the different contributions of the sea level change. It's more work, I would say, is needed. It's a little bit similar from my point of view as the discussion we have had on the global sea level rise. We were able to make already for a long time projections on global sea level rise, and I think it's only more recently that on a 100-year timescale we are getting close to closing the sea level budget. It's still some discussion going on, but there are also papers claiming that the global sea level budget over the last century is closed. And I foresee that we move in the same direction for the regional sea level changes. There is a lot of discussion still whether we can close it, but I think we will get there in a couple of years. For the future, I think this work definitely shows that we are able to do all the calculations. We are also showing that each contribution can dominate the sea level change locally, and I think for that reason, we have to continue working on all the different components in the future. And if you make a wrap-up of the results, I think it's fair to say that you may find local deviations on this time scale which are 50% below the average up to, say, 30% above the average, where you are in regions which are far away from where the ice mass changes take place, and where the steric component is also a little bit above the average of the steric component. But I think I still have some time. So this is basically what we did last year, and I also thought a little bit on sea level rise and uncertainties, and that is particularly from the perspective of the fact that I'm Dutch. And the Dutch have sea level in their genes, I think. And that is basically due to that we have had a large flood in February 1953, where nearly 2,000 people drowned. And sea level is really always at the agenda of the people in Holland. And this is a saying I took from the Dutch ministry, which was recently in the newspaper, so somewhere in the spring, which says that the Dutch forget what it is to live below sea level. Water is an underestimated political subject, so we're always discussing sea level in Holland. And one of the sayings was that the single storm which may occur once every 10,000 years can be the one from tomorrow. And I was a little bit puzzled about this statement, particularly because I think we can now we have so many data now that we can address these uncertainties. As I thought, what does it mean every 10,000 years? And because it is obviously very important, this kind of things for the Dutch coast, we also have a water law. And so by law, we have to protect our coastline to different levels of accuracy of storms around the country. And the most dark parts, which are the parts here, they should be protected to storms which can only occur once every 10,000 years. And if you talk about once every 10,000 years, you're talking about things which can occur at an accuracy level of, say, 4 sigma. So you really need to be very precise in your statements about sea level rise. So we're now working a little bit more on this regional sea level rise, and the question is, can we, based on these new models, say something about extremes, so things which cannot occur every day? And there are 2 things which play a role there. One, of course, is the wind. And on the wind, there are some statistics, how often certain storms can occur. And we have had a quite extensive modeling exercise with GCMs to see whether these storm frequencies will change over time in a changing climate. And for the time being, it's shown that for the Dutch coast, this is not going to change. And if we take that as a given, then the other uncertainty on longer timescales is dominated by the uncertainty in the ice dynamical changes. And there are now, I would say, 3 possibilities to estimate this ice dynamical discharge. And one is what I would call the deterministic approach, which is basically what is done in the IPCC report. So in the IPCC 5 report, there will be a prediction on the ice dynamical contribution to sea level, which is, I presume, Gaussian distributed. And there are a couple of other approaches which draw my attention. And one is that there has been an expert assessment, which is published in Nature Climate Change, January, I think, this year, by Johnson, Bamber and Aspinall. And that is, well, you can discuss whether you believe in the methodology or not, but from earthquakes and volcanology, they have some experiments with this type of work, and it's basically based on the idea that you ask experts on their ideas on a certain risk, being, in this case, the ice dynamical contribution to sea level rise. And this methodology shows that if you ask that to a group of experts, you get a more reliable answer than to any of the experts itself. And there are results which give a skewed distribution on the ice dynamical contribution. And there is another paper which is still in progress, which is written by Mark Sidal, which gives a kind of stochastical approach on the contribution of ice sheets to sea level over the next century. So we have different possibilities on estimating the uncertainties in the ice dynamical contributions for the next century. And if we take, for instance, the one by Bamber and Aspinall, you can see the probability on the left axis as a function of the contribution for the different ice sheets, the East Antarctic ice sheet, the Greenland ice sheet, and the West Antarctic ice sheet. And what you can see clearly is that there is a long tail to the upper end. And so this is the expert assessment. So apparently the experts do not exclude that there is a significant contribution from the West Antarctic ice sheet due to this marine ice sheet instability hypothesis, which was discussed by Katrien the previous lecture. So this you can combine, in fact, with information from the climate data, from the climate records, and I will do that in the next slide. And the same holds, in fact, for data which are based on this stochastical approach, where you can look to data of the sea level rise depending on the size and then on the observations which are available, which are mentioned here for the Greenland ice sheet. There are observations on sea level contribution from individual glaciers, For small glaciers, this is known, and for West Antarctica, it's known. And if you combine that, you can estimate what the sea level contribution would be in a century. And the interesting thing is that if you look to this left graph, where you have the probability as a function of the sea level rise, you have the climate effect only, which is then the CMIP5 result. The CMIP5 result gives a certain value and an uncertainty, and that's Gaussian distributed. So that's this black curve. And the expert assessment for the East Antarctic ice sheet, so that is based on the Bamber result, can be added up to this Gaussian distribution, but it's a non-Gaussian distribution. So you have to do that a little bit carefully. But if you do that carefully, the main thing you can see is that the shift in the median is only very small, because the East Antarctic ice sheet does not contribute much, according to this expert assessment, to sea level rise the next century. But there is a large uncertainty to the upper end, and that is shown here by this number 22. So the median is only shifting by 2 centimeters, but the 95% confidence level is shifting by 22 centimeters. And if we're thinking about events which are at the 4 sigma level, then this is a very important notion, because it means that the small events increase enormously, much more than the mean increases. And that is in this case for the East Antarctic ice sheet. For the West Antarctic ice sheet, I also did that, and you see the similar thing. The median is changing 12 centimeters, whereas the 95% is changing 52 centimeters. And we in fact need to consider 99% rather than 95 if we are discussing events which can take place only once every 10,000 years. And that is what finally ends up then in this diagram, which we consider to be very important because it plots the surge as a function of the return period. So yeah, I think it's nearly the last one. So we have this wind effect, giving that we can manage a surge level of 3.5 meters, which can only occur every 10,000 years. Then we have, on top of that, an extreme sea level scenario. So basically, our norm for our dikes is something like 4.9 meters, I estimated. But the uncertainty which we now have from the climate models, in fact, already reduces this return period to a little less than 5,000 years. And if you, on top of the uncertainty in the climate models, add up the uncertainty which we have from the ice dynamics, in this case from the West Antarctic expert assessment, then your return period is going down dramatically. And that is, I think, a thing which we really have to start considering in more detail in our future work, because this 1 to 10,000 protection levels are not possible anymore, I think. So on top of the conclusions we had already based on the part which was focusing on the climate models, we now have to consider, I think, that we need a revision of our water law or our political ideas on how we can handle sea level extremes, because I think the level which is claimed is not any longer holding, given the fact that there is such a large uncertainty in the ice dynamical contribution, and also a significant uncertainty in the climate models. There are some issues in this calculation, and one of them is that the different ice sheets are not reacting independently of each other, and we have to consider carefully how we treat that in these kind of calculations. That's where I want to end.